In this slidecast, we'll talk about the deck. Deck is short for double-ended queue. We can insert and access and remove items from either end. In the C++ standard library, deck is powerful like a vector in that we can have random access iterators. These are not supported in stacks or queues. And that's in addition to adding and removing from either end. Here are the methods and a description of them for our deck class. And many of these are similar to what you've seen in the other sequential containers. You can stop and study each of these and see that you understand each one of them. Earlier in this chapter, we saw how we could use a circular array to implement a queue. And we saw how that we could do our push and pop operations using that circular array. And we can do a similar thing with the deck. That's left as an exercise for you. Now, to obtain random access, we could consider that the ith element is at position front index plus I, assuming that I starts at 0 and sum is not larger than capacity. Now, if it is larger than capacity, then we need to wrap around using modulo arithmetic. So the index operator can be implemented using this calculation to calculates the location of the ith item in the deck. And the other functions are left as a programming project. Now, a randomly accessed circular array is part of the standard deck implementation, and we'll refer to this implementation of a deck as the class C array, or for circular array. Now, the standard library is a bit more complicated than the circular array that we saw for a deck. In the standard library, we have a circular array here that's an array of pointers to blocks of data that contain, a set of items in our deck. So the first data item is located at offset, so at offset within a given block. And the last data item is located at the index offset plus num items minus 1 mod the block size. So the original designers, they chose this scheme of an array of pointers to block, partly so that the cost of reallocation could be reduced. Because even though we have a constant time operation, reallocation is still significant when it does happen. And if we store pointers in a circular array, then the cost of reallocation is reduced because copying a pointer is a simple operation. And storing pointers to single objects could work, but allocating small objects has a significant space overhead. So by allocating an array of objects, we minimize this space overhead and we minimize the cost of reallocation. So for large collections of large objects, the deck can be used instead of the vector to minimize space overhead and the cost of reallocation. Here are the data fields for a deck, and we keep track of a block size that indicates the number of items in each data block. And here's an implementation of our overloaded index operator. We'll check for an out-of-range error, and then we'll calculate the block index. This indicates which block the item occurs in, and then a data index is an offset within that block of where it occurs. And then accessing our item is a reference into a two-dimensional array. This first index is an index into the circular array that points to blocks, and then this is an index into a given block. Here's an implementation of pushback. This first line computes the current capacity, which is the number of blocks pointed to times the block size. So this is the total capacity of all the current blocks that we have allocated. And if they're all full, then what we need to do is we need to push a new block. This will be sort of an empty block to the end of our current, array of pointers to blocks. That's what this pushback does. So here we're pushing a new block to the end, and then we increment number of items, and this is a pointer, refers to that last block that's pointed to by our the first level array, and it adds this item to the first location in that block. Here's our pop front method. So we increment the offset, and if our offset is equal to a block size, then we've wrapped around and our offset now, the front is now into the next block. So we're going to delete this block at the front, and we'll say pop front. And what this is going to do is going to remove that block from the front, and we'll adjust all of our pointers to blocks up to the beginning of the data, and we'll reset offset to be 0. And in this case, num items, and then we decrement num items. And that brings us to the end of this slidecast.